Welcome everyone to today's TransferLab seminar. The TransferLab seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning. And today we have a talk by Kristof Schröder. Kristof is a research engineer at the appliedAI Institute for Europe, and he will talk about second-order information and applications. So in particular, second-order optimization and also methods in data valuation. Okay, so Kristof, please.
All right, thank you. Welcome, everyone. Thanks for coming. So I will tell you a little bit about second-order information and applications in this talk. The nature of this talk is more an overview talk. Like, I will not go into very mathematical details, but I hope you still get the idea and the intuition behind it. And it will cover different sorts of applications where the mathematics behind is actually similar, but different sorts of application areas. Like, to start, I will give you like a short introduction about why second order information in optimization, why is it useful, or what are the obstacles when my model starts to get big, what are the problems I encounter, that you get somehow a geometric intuition why second order information is useful. And then I will talk about 4 different kinds of applications. Like, the first 3 are more related to optimization, where the last one, the inference functions, is a concept for data valuation, like an area we are explicitly working to provide a stable software and performance software. And I will show you how this is related to second order information. And lastly, I will give a short overview about the software, available software for the algorithms I talk about, and this will be the talk. All right, so first question, why? Why should I consider to include second order information into my algorithm? So if you think of an optimization, like you're the guy on the hill, right? And you want to go down somehow, it's helpful to include somehow knowledge about the geometry in the sense of curvature of this landscape into your process, right? Just having the direction of the steepest descent might not be sufficient to go down. Yeah. So think of, like, you may end up here, right? If you go too far. The reason is, like, the direction alone is not sufficient to give you enough information to go down efficiently. How can this help us? So including this knowledge can reduce the number of iterations you have to do in order to get a certain result, to get a certain error. And moreover, it can improve the quality of the result, so that you get a local minimum, which is in a sense better. So having smaller validation loss, so to say, than you would have with first order methods only. All right, so small recap, gradient descent. So I have my differential smooth function. Like, for now, think of this as like a strongly convex one, and I want to go downhill. So like you see in this picture, and what I do, I somehow follow the gradient, which is the direction of the largest descent. And given this, like, a step size, which you can like compute by some rule, I go down. And if my loss landscape is like well behaved, well conditioned, so meaning it has somehow homogeneous curvature, it actually looks like this. This is fine, right? So I still get a linear convergence rate, and the convergence depends on the condition number of the Hessian at the minimum. So what is encoded in this? So if I have very heterogeneous curvature, this Hessian will have a very large condition number. I have in different direction, I have different curvature. It's quite heterogeneous, and this will increase the condition number of the Hessian, and this will slow down the convergence of the gradient of the first order method, right? Okay, so what can I do about it? So if I'm in this case that I have a loss landscape of this type, I can include this knowledge, right? Knowledge in the sense of I include the Hessian information into my descent process. And well, this is known as Newton's method, right? That you somehow precondition your gradient with the inverse Hessian. And why does it help? Well, think of this as a preconditioner. So meaning, if you're close to the minima, the condition number is small. If you look at this product, meaning you somehow make this problem more well-conditioned than it is. What you get is, instead of a linear convergence rate, you get a quadratic convergence rate. This is fine, but now what happens if the function I would like to minimize is some sort of this? So you have a parametric model, like a neural network. Think of many parameters, some loss function, and what you would like to minimize is this expression. What are the problems? Now I use like gradient descent or Newton's method. What would be problems I encounter? First point, this one is highly non-convex, right? So if I just do a Newton method, I might end up in a maximum, not a minimum, right? Because it's looking for stationary points. And if I'm not convex, it's not ensured that I will end up in a minimum, actually. Well, okay, problem. But say we are somehow in an attraction area of a minimum, of a local minimum. As I said before, if I have very heterogeneous curvature, so saying this loss landscape is highly ill-conditioned, I somehow have to include information about it. Because we've seen the first order method is slowed down by heterogeneous curvature. So I somehow have to correct this. But the memory costs are gigantic. If like D is large, think of vision models or transformers or whatever, I can't store it. It's quadratic in the dimension, in the number of parameters, and the naive inversion. If you look back to say computing this, right? Naive inversion, computing the inverse, is cubic in complexity. So no chance, right? Boom. We would like to still use somehow a second order information to get these additional curvature information to somehow speed up our optimization. What should we do? We somehow approximate these preconditioned gradients. So not compute them exactly, right? But having an approximation of this. And there are several strategies you can follow doing this. So first of all, you would never like compute the inverse, you would somehow do an implicit inversion, solving this equation. You can restrict to blocks. So think of, you have a neural network with layers, right? You can restrict the inversion per layer. So you get actually a block diagonal approximation of the Hessian. And in the extreme, you can just say, okay, I'm just looking at the diagonal, right? You can add randomization. So you would do this anyway, because you somehow, even if you use like a mini batch strategy, you somehow already have randomization in it, but you can even go further. And what you have to add often is like a smoothing step to somehow smoothen this randomization and getting a stable algorithm. You can use properties of the Hessian. So what's observed is that for large networks, for deep networks, the Hessian is approximately low rank. So what does it mean? I have like some few large eigenvalues, but then I have a fast spectral decay. So actually the information, the true information, is encoded in a very small number of directions. Then I can use different decomposition of the Hessian, and this is what's like used as Gauss-Newton approximation and Fisher information, which are in some situations equivalent, which simplifies the Hessian in some kind, and we can use any kind of this and you can combine them, right? This is somehow the way to tackle this scalability problem. On one side, you have the memory, which you have to reduce, right? Like quadratic is impossible, right? So you have to keep linear memory. And for the runtime, it should be linear in the best case as well, right? so that you have like comparable computational costs than you would have in a first order method, right? Okay, let's look at an example. Yeah? So large language model pre-training. Yeah? What I mean is like the big models and not doing a fine-tuning, but really train them from scratch on large data sets. This needs heavy compute, right? And often the state-of-the-art solver which is used is Adam. And we can ask the question, so how can we incorporate second order information that we reduce the number of iterations compared to Adam, but not to the cost that we increase the overhead per iteration dramatically? If we would in each iteration like compute the full inverse Hessian vector product, this will be large overhead per iteration, which would neglect the advantage of the reduced iteration number. So this has to be in a balance, and the memory footprint should be like comparable or in best case the same. Motivation, yeah. So think of like we have somehow these non-convex different curvature in different directions. And so what can happen is that like the Newton method could not go to a minimum, but to a local maximum, right? So we have to somehow avoid this. We want to avoid like this zigzag. This is what you observe when you have heterogeneous curvature and use first order methods. This heterogeneous curvature will give you a path like this. And we want to include the second order information in a way that we somehow follow nicely this curvature and go down to this minimum. A recent publication from like 8 months ago, I think, introduced Sophia, second order clipped stochastic optimization. And actually, it's quite simple what they do. What they do is they introduce a stochastic estimator for the diagonal, which is quite cheap to evaluate, meaning memory-wise, you only have one additional vector in the size of your number of parameters, right? Which you have to keep track of. Then, like to handle the stochasticity, what you do is smoothing, right? This is what you do in Adam as well. In Adam, you also keep, like you also have two vectors which you keep in memory, which is like the first moment and second moment. So the memory consumption is the same. Then you do the following, right? So you do a simple gradient computation. You smooth exponential moving average, smooth the gradients. Every 10th iteration, or what you decide, you estimate the diagonal of the Hessian. This you smooth as well using an exponential moving average. And then you update. And the only thing which comes in addition is you clip coordinate-wise to handle the like negative curvature. So what you would have here, right, to avoid something going in this direction. So it's a very simple, actually a very simple procedure, but the results are pretty remarkable, at least I would say. So they have examples for large language model, GPT-2 training on open web text. What they observe is compared to Adam, they have halving the number of iterations to get this comparable validation loss. Half the number of iterations, you get a comparable loss on the validation. Moreover, with a much smaller model, you get a comparable validation loss. I think it's hard to see, but the distance between those points increases the larger the model gets. So this optimization has a better scaling law, which means the minimum you get from this optimization procedure is a better one, so it generalizes better to the validation. But important, what is the cost for this? As I said, we have the same memory cost, identical to Adam. There is an overhead per iteration, which is smaller than 5%, they say. Which means actually the total wall clock time is halved. And now think it's large language models, right? Your training costs like 10 million. This means you save 5 million by using a different optimizer, right? And which is a simple one. There are not many parameters, right? So it's easy to use. Like you carefully include the second order information by a stochastic estimation every 10 steps. So you could say it's quite sparse what you provide regarding second order information, right? But the result is quite remarkable, I would say. Okay. Different use case. So like I have a pre-trained large language model. I would like to fine tune it on like my data set or for a specific task. When doing this, often I have a limitation of compute and memory both at the same time. So I might not have like a large GPU cluster which I can utilize to do this fine tuning, but maybe just a workstation, yeah, or something else. The memory need starts getting more important. Also, very recently there was an work on zero order optimization. What is the problem regarding the memory? It's the backpropagation. You have to have the full computation graph in memory, and this is the biggest memory consumption you have. So, what to do? Get rid of the backpropagation. Use something which only uses forward paths. So you do not have to keep this computation graph. What they show in this paper is like they have 12 times reduced memory consumption, so that you can fit like a big model onto one GPU, for example, instead of like 12. But the problem is the zero order methods might converge very slowly. The reason for this is like, look at this. This is somehow what they use instead of the gradient, like the gradient you would get from the backward pass. They use these so randomized finite difference, I would say. So yeah, like if you have seen some lectures from numerics, like this is somehow a centralized finite difference, right? And this you randomize in the sense of the direction, and this you use as a surrogate for the actual gradient. What's the problem? Well, first of all, it's randomized, so this will add some noise, right? You have a mini batch, this will add noise. Plus, there's a numerical effect which isn't mentioned in these papers, which is called catastrophic cancellation, numerische Auslöschung auf Deutsch. So when you have like two values which are quite close to each other, which is the case, right? If the epsilon is small, then you cancel like the valid floating point positions, and the only remaining parts are like the numerical error parts, and what you get can be super noisy due to this cancellation effect. Yeah. So what can you do? Well, you can average this, right, to get it, make it more stable, like average like over different samples from the distribution, but this comes at a cost as well, right? A different approach is, can I somehow include an approximation of the second order information into this process? And again, you see, like it's the similar loss landscape. Yeah, we have our Adam, well-known friend, and then we have like the zeroth order method without second order information, which goes somewhere, and maybe going around, and sometimes like very late, going down to the optimal point. Like 2 months ago, a small modification of this zero order scheme was published, which is called like Hessian informed zero order optimization. This is like an illustration of the paper. Okay, what's the idea? So I somehow have to control this randomness, and what they do is they iteratively refine an approximation of the diagonal of the inverse Hessian. And you see, this is the difference. Instead of purely sample Z and that's it, we map it by these approximation. And the key is the overall computation requires 3 forward passes of the model to get these. Yeah, so like instead of for the zero orders method alone, we would have 2. Now we have 3, plus we somehow get an approximation of this curvature information included. Yeah, then like they test this on several sets, and what you get is you get a reduction in the number of steps while having somehow comparable computation time per iteration. Completely different area, physics-informed neural networks. Think of like you have a PDE, which is like defined in an like open subset, and you have boundary conditions. What you can do is you can train a neural network on a loss, right? So you get a discretization of your domain, and you can train a neural network to actually solve your PDE. What you have like a term which corresponds to the differential equation itself and a boundary term which solve this equation. So minimizing those, you hope that you have like your function U satisfies this differential equation. So what are the key observations? First of all, like pins are hard to train. Plus, you must achieve a near zero loss to really get a good solution to your PDE. Why is it hard to train? The loss landscape is very ill conditioned. Yeah? So I'm saying like the hashing in your optimal solution has a super large condition number. Yeah? So you have heterogeneous curvature, and including a second order information can improve this conditioning significantly. So these are like the observations they do in this paper. Yeah, it's also very recently, 3 months ago, 2 months ago. Very nice, well-written paper. Many insights, like, for example, so why is it ill conditioned? Yeah? So what they do is 3 different types of PDEs. They look at the Hessian after some time of iteration using Adam plus LBFGS. They look at the spectrum, at the spectral density of the Hessian, like unconditioned, right? And then preconditioned with the next quasi-Newton update, which you would have in the LBFGS. So in this algorithm is a quasi-Newton method, which replaces the inverse Hessian with a way easier to compute matrix, so to say, which gets updated. And what you hope is that these matrices somehow reduces the condition number of the Hessian at the optimum. And this is what you observe, yeah? So instead of having like this large range, yeah, from 10,000s to 0, you shrink it to this range, the spectral density. And this means you lower the condition number, right, of your, because it's, you say it's like lambda max divided by lambda min, yeah, the condition number. That's nice, all right. But what you see as well, looking at this picture, is you have also a quite heavy spectral decay. Yeah, so you have very few large eigenvalues, and then you have many, many small ones. Yeah, I think like you have here, you have a few large ones and many, 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 many small ones. Meaning, yeah, your spectral decay is quite fast. It's accessible for a low rank approximation. And this is what they propose in this paper, because what they observe is that like this classical quasi-Newton method, which somehow already includes approximative second order information, stops early due to the construction of this. Yeah? You have to make it stable, you have to somehow control your step sizes in a specific way to somehow keep the quasi-Newton matrices positive definite. And these conditions will lead to an early stopping. Yeah? So the loss is under-optimized. But this is a problem because we have seen before that you need to achieve a very low loss of your loss value of your combined loss to have a valid solution of your PDE. Okay, and what they say, okay, then we have to do a different approximate Newton step, which allows for further progress. And due to this observation, like the spectral observation they use a low-rank approximation to the Hessian, which is coming from a random projection, so to say, of the Hessian. It's now called Nystrom approximation. This is positive definite by construction, and they use this as a preconditioner for conjugate gradient to solve this one, right? This is what we want. And if you replace this one by something which is positive definite, you can use a conjugate gradient, right? And this you can precondition to improve convergency. If your matrix is approximately low rank, this works quite well. If your preconditioner is built in this specific way. And the final algorithm looks like this. So what you do, you compute these Nystrom approximation, that is low rank approximation. This you can do in an efficient way, like you compute the factored decomposition, because then you can compute the inverse action quite easily. Then you do a preconditioned conjugate gradient. You choose a step size by a simple rule, and this is your algorithm. And the update, the update of the preconditioner, is only every f steps. If you have like a little bit of knowledge about BFGS and optimization, you would say, okay, this algorithm is more expensive than the LBFGS, right? But in this case, it's not about like reducing the iteration time, but achieving a solution which has a much lower loss to actually solve your PDE. And this is what they show. So this is a log scale. They propose first use Adam to make as much progress as you can, switch to LBFGS. When this doesn't give you any more, then switch to like this most expensive but more powerful solver to get like the last bit. And by last bit, I mean like orders you need for your solution being a solution to the PDE. Solution of the minimization being a solution approximately to the PDE. All right. So until now we have seen like 3 different like optimization problems, different in the sense like what is the most important part for this optimization. Like the first one was speed, because speed is computation time and this is pure money. And the second case was more like, okay, I have to reduce the memory somehow because my fine-tuning environment isn't that powerful. And the last one is about the quality of the solution. In this case, I'm willingly to pay a lot of computation to get a good solution in the end, because I need it, because this construction, the physics-informed neural networks have this property, and I need to handle this. So coming to the last example, which is something we work with a lot because we are like implementing software for this and having this as an open source repository on our GitHub. It's called inference functions. And what you would like to answer is the question, how can I measure the influence or estimate the influence of a single training point on model parameters or model output on test points? There's a concept which is called inference functions, which computes this estimate, like this is a number, which computes this estimate as this product. Now think of this, it's somehow, you have these gradients, and now you can compare gradients. Do they align well? And this well aligning, this measurement of well aligning, you weight by the geometry of your loss. So this is how you can interpret this. And again, what is the bottleneck? Well, the computational bottleneck is the computation of this one. Very recently, there were methods which scale better than like naive solution to this. We have heard a talk about this already in the previous series. So eigenvalue-corrected Kronecker factorization, which uses many sorts of approximations. This is already implemented in appliedDVL, which is the software package we are working on in one of our groups. So as I said, we had a seminar talk about this. We have a paper pool available going more into detail of this. We have an implementation. So these, in the last example, these Nystrom preconditioned conjugate gradient, right? You can use for computing the inference function values as well, right? It's the same expression. So you can use actually the same algorithm somehow. And we implemented this for in appliedDVL, and this will be in the next release. We'll see, maybe tomorrow. And the last one also, like in the last half year, I think, has the potential to scale very well in the sense of computation, because it makes some very rough approximations, so to say. But it's not clear why, like, the relation to the true solution is, at least to me, it's not completely clear. But still, we would like to make this available through our software package appliedDVL, so it can be used. Finally, let's talk a little bit about software. So the Sophia algorithm is implemented by the authors as a torch optimizer, inheriting from torch optimizer. But there is no package for this. Yeah? So you have to get the code and include it into your repository if you would like to use it. There is an open issue for packaging this, but this is stale for like several months now, I think. The zero order algorithm is implemented by the authors of the paper as well. It's implemented as a Hugging Face trainer. Again, no package. Same for the Hessian informed adaptation, implemented as a Hugging Face trainer, no package, plus the code is, at least what I've seen quickly, is like research code. And the physics informed neural network application, and in combination with the Nystrom approximation and conjugate gradient, is available here, which and also implemented as a torch optimizer. And again, it's no package. And so it's very recent. So all of this stuff is like from the last 8 months or so, 8 to 10 months. So there is no packaging by now. All right. Thank you. I would like to hear your questions if there are any.